component seismic. So this topic is my PhD thesis or research work. So during my research work, I used 3C seismic data. Okay, 3C means three component. Okay, seismic data. So when we were talking about seismic data acquisition, I talked about types of data set like CDP, that is common depth point, CMP, common midpoint. Okay, and on split spread, types of geometry. And now we will discuss more about wide angle seismic data. Wide angle seismic data means the area of coverage of the seismic offset will be more than 200 kilometers or 200 to 600 kilometers. Even, I mean to say, it should be always more than 150 to 200 kilometers. Okay. So that is why it's called seismic wide angle seismic data. Okay. So it's always and wide angle seismic data are of two types. Okay. One is single component, that is conventional P-wave seismic data, and another one is three component seismic data. Three component means, see, when you see a earthquake whenever you see a seismograph. So one second, let me switch on my video. Yeah. One second. So what happens is, like whenever you see a earthquake data on seismogram, so it will have three traces. Okay, so like this will be vertical, and this will be in northern direction, and this will be in eastern directions. We have already discussed this during seismic data acquisition. So it's a three component seismic data. So it's a not earthquake data, but it's an active seismic data. Means we used explosive and other means to just seismic. Yeah. Any questions? If not, please switch, turn off your mic or switch off your mic. Please turn off your mic. Please turn off. Yeah. Okay. So the thing is, we have used explosive in certain pattern, so as to generate P and S wave both. Okay, and for along the three components. Okay, using a three component geophone. Okay, so three component geophone, I have already shown that in the when we were talking about seismic data acquisition part. Okay, so see, normal geophone has only one spike. Okay, so it will only measure the vertical motion of the ground, means the jet component. Okay, so that is why it's called P-wave single component or the vertical component. But in case of three component geophone, it has three spikes. Okay, it will be like three spikes will be there, and all the three spikes will go inside the earth, and they will record ground motion in vertical and horizontal fashion. Yes, that is why it's called three component. Means it will record all the three components of the seismic data. Means like the vertical ground motion and the two horizontal ground motion. Okay. So that is why it's called three component seismic data. Okay, so we have used three component wide angle seismic data to image the crust using seismic inversion or ray trace inversion, which we will see in the coming slides. So first I will talk. One second. Sorry, please, one second. Yeah. So before going into that, I'll discuss the research highlights. How three component seismic data is much more useful than a conventional P-wave single component seismic data. So from three component seismic data, we can have crustal velocity model for P-wave and S-wave as well. Okay, we can make a density model. See, from P-wave velocity information, we can compute density values and I'll not talk about heat flow modeling because it's out of the scope of this talk. But crustal velocity model and density modeling, we will see how to do, how we can do. Am I the only one not hearing anything? Hello?
No, we can hear you.
Can you guys hear me?
Yes, we can.
Yeah. So three component seismic data will help us in making crustal velocity model for P wave and S wave, and we can also make density model, crustal density model, so as to understand the variation of density laterally and vertically, and it will help us in predicting the lithology of that area, what kind of mineral or what kind of rocks are present there in that particular area. I can hear. I think the fault is. So, and from three component seismic data analysis and modeling, we were able to delineate or demarcate or find major shear zones like Chitradurga shear zone, and we will see what kind of gravity. See, you have to study gravity as well. So we will be seeing the gravity structure or Booker gravity anomaly structure at these shear zones like Chitradurga shear zone and Babudan shear zone as well. So it's a bonus for you guys that along with seismic method, you will be learning about the gravity modeling as well. Okay. So to image major granitic batholith like closed pit granite. So we will be seeing the gravity structure of closed pit granite and the seismic structure of closed pit granite. And we'll be also delineating the low velocity layer, which we talked yesterday. See, I talked that the uppermost layer is always low velocity layer because of the weathering. Okay, but we'll find LVL in subsurface as well. Okay, and we'll also be able to delineate the compositional changes laterally and vertically in the same area using three component seismic data. Okay, and we'll also be able to delineate the underplating layer. So what is an underplating layer? So underplating layer is highly mafic rocks which intruded from the from asthenosphere as molten lava and then spread over moho. Okay, in the crust it spreads and it forms a layer. So that is called underplated layer, and it's most of the time it is mafic in nature. So we'll be seeing the velocity structure of that particular underplated layer, and as well as the gravity or density structure or density value of the underplated layer. Okay. And finally, from tectonic, and we'll be talking about tectonic and geodynamic evolution of the Dharwad Craton. But I'll be talking only about the tectonic settings of the Dharwad Craton because geodynamic evolution is out of the context for this talk. Okay, but I'll try to explain how I developed this geodynamic evolution model for Dharwad Craton. I will discuss in a little bit about that as well. So the main objective of today's talk is to find the subsurface geology and tectonic model using three component seismic data to prepare P wave velocity model, S wave velocity model, VP by VS model, and Poisson ratio model. See, now I have P wave velocity model, S wave velocity model. Okay, so from combining P wave and S wave velocity model, we can compute Poisson ratio, which gives what kind of lithology is present there. VPVS also gives the helps us in delineating types of rocks and types of what kind of lithology is there. So Poisson ratio and VPVS are very much important for delineating any kind of lithology in that particular area. Okay, whether it's felsic or mafic or we have quartzite kind of structure or an arthosite, means different types of rocks will be able to delineate with the help of P and three component seismic data. And we will also talk about seismic anisotropy, how it is important and why it is necessary for us to study seismic anisotropy. So today's talk is going to be very interesting because we'll be talking about seismic modeling and seismic anisotropy and gravity modeling as well. Okay. And we'll also be talking about, we'll see the signature of seismic velocity to image shear zone like CSZ and BSZ and batholith like close-pit granite. And we'll also see the extension, special extension of how wide it has expanded or it's expanded in the subsurface. We'll see that as well. Okay. So which cannot be done properly with the help of seismic data processing. Okay. So we'll be doing this by seismic data modeling. Okay. We'll also be able to delineate Moho configuration. See, for crustal studies, the offset are very large, means of 150, 200, or even 600 kilometers, so as to image the crust up to Moho or below Moho, like up to 100 kilometers we can go up, with the help of active seismic data. Okay, and that mainly depends on the what kind of how much amount of charge or dynamite or explosive we are using. Okay, so now suppose if my objective is to image only up to 5 or 10 kilometers, so I'll use vibrosis and thumper. But if I want to image full crustal up to Moho, I'll have to use explosive of among more than 1,000 kgs of dynamites or TNT or explosives to image up to 50, 60 kilometers of the depth below this in the subsurface. Okay. So moving on to the next slide. We have already talked about the types of seismic wave, okay, and what kind of seismic waves are there. So we have two body waves, P and S. We have two surface waves, Rayleigh and Love waves. So we'll be talking about only body wave in this because surface waves are important for near surface geophysics. Okay, so that's a different branch of geophysics and seismic method. Okay, and we also see seismic method because see we have the control about how much charge we should use to image the subsurface. So based on that, we'll give the, now suppose if I provide more energy, if I blast huge amount of dynamite or explosive, so more energy will be generated and more energy will travel up to long distance. So the resolution of the subsurface or the imaging of the subsurface becomes more precise using seismic data. And by studying the seismic data, we can get the in situ physical properties of the subsurface. Now, what happens, what geologists do, they take the sample from the subsurface, like see if there is a drilling is going on, so they will take the sample from that site and they will bring it to the lab, and then they will try to create an environment or a physical scenario of that. Now suppose if the rock is present below 10 kilometers of the earth, so they will try to create a scenario where so as to match the in situ environment of that particular rock in the lab, and they will try to study the different properties of that rock in that particular temperature and pressure. Okay, so as to match the actual scenario. But what happens? It's almost impossible to create such kind of scenario in the lab. Okay, so that so whatever lab experiments which we do or geologists do on a rock sample, we get somewhat similar kind of readings, but not actual readings because environment has changed. So seismic method helps us in delineating those physical properties, in situ physical properties of that particular layer of that particular rock. Okay, and we get a very precise result output. And as we know, P waves are also called compressional wave and primary wave, and they are first to reach the receiver. And the P wave velocity is given by this lambda plus 2 mu over the rho. Okay, and the whole parameter is under square root. Okay, so this is rho is density, lambda is Lambert's constant, and mu is the shear modulus, k is compressibility. And so this is the formula for what do you call, calculating P wave velocity, and this is the formula for calculating S wave velocity, that is mu by rho. Now from these equations, what we learned? We learned that a P wave can travel in fluid media as well, because now suppose fluid media, the shear modulus for fluid media is 0. Okay, so even this whole term becomes 0. So lambda and rho will define the P wave velocity in case of fluid media. But S wave, what happens to the S wave? See, in fluid media, this mu becomes 0. That means this whole Vs becomes 0. That means S wave cannot propagate in a fluid media. So this also helps in delineating what is called subsurface lithology. Now suppose if a layer, now suppose there is a shell and sand, there's an alternate shell and sand is there. P and S wave velocity, P wave velocity will be almost similar for shell and sand. Okay, but when we talk of VP or VS or portion ratio, we'll be able to differentiate between shell and sand very precisely. How we do that? Now see, now suppose sand has porosity and there is fluid, lots of water molecules is in that fluid. So when P wave passes through that, the velocity will decrease. Okay, but when S wave passes through that, so what happens? S wave will only move through the matrix, but not through the pores filled with water, because S wave velocity becomes 0 in that in that pore which contains water. So that means S wave velocity will decrease drastically, very drastically. So we can use VP or VS to discriminate the fluid bearing zone or oil and gas bearing zone. Okay, because see, P wave velocity will decrease, no doubt, but S wave velocity will decrease drastically, and that so that gives an impression of the presence of fluid in that particular layer or a zone. Okay, and it also helps in imaging the many fractures, because see, even if there are numerous fractures are present in the subsurface and for one particular layer, suppose. So what will happen in that fracture? There will be it will be filled by air or any kind of water molecule. Okay, so S wave velocity analysis will help us in delineating those fractures. Okay, so that is why study of S wave becomes very, very, very important for oil industry. And we have also any questions? If not, if you don't have any questions, please mute yourself. Kindly mute yourself. Yeah. We have also in previous sessions we have talked about reflection seismic method and refraction seismic method. Okay. So yesterday we talked about the reflection seismic method and how we process the reflection seismic data. Today we'll be seeing wide angle reflection or refraction seismic method. Okay, and how it is useful for delineating the structures and velocity zones, LVL, and other types of orientation of the bed. Not important. This is not important, so I'll not talk about this. Okay, let me talk about this a little. Dharwar craton is a very old, one of the oldest Archean craton, and now it has become stable, but earlier in the past it has gone through many volcanic activities and orogenic movement. So it has a very complex geology, which we will see in when I will talk about the geology of that area. See, for every geophysicist, the idea of geology or the concept of geology should be very clear, because at the end of the day, what we do is we try to interpret our seismic data or geophysical data in terms of the geology of that particular area. So having an understanding of geology is very much important for every geophysicist. Okay. So, okay. Now, as I said that, keep this here so that we don't find any problem with this. So Archean rocks has generally the age of the Archean rocks which is found across the globe is around 2.5 billion years of age. 2.5 billion years of age. Okay, and Archean rocks are mainly metamorphic or igneous type, and they mostly have granite, gneiss, and greenstones. Means they are dominant Archean rocks around the see wherever there are Archean cratons around the globe. They all are dominated by this granite, gneiss, and greenstone types of rocks in that particular cratons. Okay, and so the most common association of rocks in Archean cratons are granite, greenstone, granite, gneiss, greenstone, which I have already discussed. Okay. And as I said that Archean cratons now they are stable, but in past they have gone through several rifting due to volcanism and plate motions and tectonic activities, orogenic movement. So you'll always find shear zones associated with Archean cratons. There will be fold belts as well. Okay, and because of folding and faulting, you'll see that rocks of that particular Archean craton has metamorphized. Okay, so this is the profile along which the data has been acquired, and this is the Dharwar craton, and it has been divided in WDC, that is Western Dharwar craton and Eastern Dharwar craton, and they are separated by this black line, which you can see. It's a major shear zone. It's called Chitradurga shear zone or CSZ, and there is a major batholith exposed on the ground, and it's called close pit granite. Close pit is a name, and it's a close pit granite. And you can see how complex the geology is. We have Chitradurga granitic belt, okay, greenstone belt. We have Babu Budan greenstone belt. We have peninsular gneiss of different age. We have, this is also the peninsular gneiss of different age. Okay, so this area has been studied very widely and very vastly by geological and geophysical methods. And why it is why this area is important, or why the study of any area is important with respect to geology and geophysics. See, we cannot go everywhere conducting geophysical survey because it's very costly affair. Okay, so what our objective is to find mineral or oil bearing zone. So that makes one particular zone very important to study, so as to so that we can exploit the natural resources from that area. That is why we conduct geophysical survey. Okay, and because of that, keeping that in mind, Dharwar craton is a highly rich in mineral zones, and it has many gold mines. Okay, many gold mines, and they have kimberlite formations as well, which contains diamonds. Okay, so from mineralogical perspective, study of the Dharwar craton becomes very much important. Okay, that is why lots of geophysical and geological study has been conducted in this. And the black line which you see, it's a 200-kilometer black line seismic profile. Okay, 200-kilometer long seismic profile. Okay, and it has total of 7 short points, and each short point has a interval of 40 kilometers. Means, see, if I blast this short point, so and it should charge for this, the explosive for this is around 1008. We have used charge of around almost 2000 kgs of explosive material has been used to cover a area or a profile of 200-kilometer long profile. Okay, so for this for short point 1, short point 7, short point 1 is here, and then short point 7. So for each short point, we have covered a 200-kilometer long profile, and we have used a huge amount of explosives so as to cover the full profile. Okay, and the interval between the short point is 40 kilometers almost, and the geophone interval was around 400 meters. Okay, so there are lots of geophones were used. Okay, for this, and 3-component geophone was used rather. This is a simplified stratigraphy of that area of study under the consideration, which we see here as we go down how the lithology is changing. So this is a simplified stratigraphy, so I'll not go into this, and now I'll directly move into the methodology, what kind of methodology I have used. Okay, so this is this is this is how a three component seismic data looks like. Okay, so here you see it's the Z component, means vertically down component. Okay, and this is the R component or radial component. One of the, see, this is the fashion of acquiring the data. So this is the vertical component, that is Z, and one of these two horizontal component becomes radial and the transverse. So radial is denoted by R and transverse is denoted by T. So you learned something new, that there is a three component kind of data set is also available, and we can acquire that and we can work on it. So you can see here the offset is almost 200 kilometers, almost 200 kilometers. For this is for only short point 2 which I am showing. Okay, so this is the Z component, this is T component, and this is the R component. Do you see any kind of difference in these data for the same short point? Can anyone tell me what difference you can see in this data for the same short point from all the components? Please unmute yourself, and if possible you can answer. Okay, if you can't, then I'll explain what. See, can you see the phases here very clearly? The refracted phases and the direct arrivals, and this is the reflections. Can you see very clearly? Yes or no? Or type, just type. If you can't say, then type. Can you see the refracted and reflected phases very clearly in this radial component when compared to this Z and T component? Right? Okay. So see, and one more thing. So as I said that P wave, three component, this data set has P and S wave as well, both. So this, the first arrivals which you see here is P wave. This is P wave. Okay. This is P wave refraction and reflection. And this, the dark line which you see here are S waves. Okay. You can see here also, these are S wave. Okay, and you see the ground rolls as well. See, these are the ground rolls. These are ground rolls. Okay, these are ground rolls. So what we have P wave, we have S wave, and we have noises as well. So this is the raw data. Okay, and once the data was processed, see, okay. So what happens for a three component seismic data which is acquired in the field, the data acquisition will always be with respect to the geographical coordinates. That means the vertical will remain vertical, but the horizontal components will be acquired in terms of north and east. So the data acquired in the field will be vertical, and then northing, and then easting. Okay, and but that doesn't serve our purpose, because when I load the data, I'll not be able to do anything with the data. So that is why what we have to do is we have to rotate the data with respect to our profile. Now this is north, okay, and this is north, this is east, and the vertical remains the vertical. So my profile is azimuth of my profile is this way. Okay, so if I'll keep a pointer here and then I'll draw north and then I'll draw east. So the data will be acquired in northing, horizontal data will be in northing and easting. So I'll have to rotate the data in clockwise fashion so as to bring the northing with respect to our profile. We'll rotate the data in clockwise direction so as to bring the northing in direction of our profile. And so northing becomes radial, which is along the profile, and easting becomes what? Transverse, which is perpendicular to the profile. Okay, so these three components will always be orthogonal to each other, means at 90 degrees with each other. Then what happens? Now the data has been rotated with respect to our profile. So now the data is ready to work. So after the rotation, we'll do seismic data processing. We'll process the data to a minimal extent so as to remove most of the noises. So we'll process the data to remove ground rolls or any kind of compensate for the spherical divergence correction and attenuation of the decrease in the energy. So we'll do all those preliminary steps. It is called pre-processing of the data. So these were the pre-processing, preliminary steps before modeling. Once the noises have been removed to an extent, the data is good for modeling. So this is the work chart or flow chart for. This is the 1 second. So this is the flow chart for modeling the data. See what happens. We took the data from field. We rotated the data. We made short gathers. We applied geometry. We did spherical divergence corrections. We did static corrections. We applied deconvolution and filtering to remove to suppress ground rolls, effect of ground rolls. Okay, so this is called pre-processing of the data. So pre-processed data is taken, and then, as I said, these are the phases like direct arrivals, refractions from different layers, and then the reflections. So what we have to do is we have to pick the phases. Okay, we have to pick the phases. You see here, this is the offset in kilometers, and this is the time. Okay, this is the time in in seconds. So what we do is we pick the travel time, or we pick the phases. Okay, so which we will see in the coming slides. So we pick the phases, and once the phases are picked, see, we pick the phases manually, and human error is bound to happen. See, I can pick wrong phases as well, correct? So we provide some kind of uncertainty that, okay, up to 25 milliseconds, picking of phases for near offset. If I can make mistakes, so for that I'll keep plus minus 25 milliseconds of uncertainty or error boundaries, because means, now suppose this is the phase and this is the time error I have given. So even if I pick between this, so it's acceptable, because I cannot be perfect like a computer can be perfect, but humans can't. Okay, so we have to be cautious about the uncertainty or error in picking. So we have to provide that information from beginning, and then we make initial 1D velocity model using damped square inversion. Okay, and then we make a pseudo 2D model from, see, for every initial 1D velocity model, what for each short point we'll make 1D velocity model, and then for each short point, and then so I have told 7 short points, so 1D velocity model for all the 7 short points will be there. So I'll connect that wherever there is a break in the velocity, so I'll connect those dots, and I'll make a pseudo 2D model, and I'll use that pseudo 2D model as a starting model, and then I'll refine on it using ray trace inversion to get the final. We'll trace the rays, like we'll generate rays through the model, and we will see the density of that model of the rays generated in that particular layer, and based on that we'll do ray trace inversion, and then we'll make the final model, and keeping in the mind see, I give uncertainty for phase picking. I'll have to give uncertainty for model also, like I'm making a model. See, this is the model I have made, suppose. So I'll give the depth model of suppose 500 meters or 1 kilometer plus minus. So it could be in this particular zone itself. Okay, and then this is assessed by a normalized misfit parameter. Now suppose if my parameter, or if my yeah any questions? Any questions, please? If no questions, please kindly mute yourself. Yeah. So what happens is we have to give a what you call error estimate for the model. So we give, and that is given by chi-square, which you see here. It's called chi-square. So if and it should always be closer to 1. It can be between 0.7 to 1.5. If it is between 0.7 to 1.5, that means it can be acceptable. That means my model is acceptable. Okay, and if it is 0, that means I have overfitted the data, or if I have manipulated the data, that means I have manipulated the data to match the actual fit. Okay, so this is incorrect. And if my chi-square value is more than 1.5, that means I have not done the picking correctly. So again, I'll have to go back for phase picking, and then again I'll have to phase picking as well as model parameterization of depth variation and the velocity variation I have to make. Underfitting and overfitting. So it's a kind of iterative process, means hit and trial. That means we have to do forward modeling and inversion along simultaneously. Means we have to check the model and the data simultaneously. So what we do is we do forward modeling and inverse modeling at the same time to get a final model. Okay, and then we do model assessment. Model assessment means we check the resolution of the model, we check the density of the ray coverage. So if my density and resolutions are good, that means my model is correct. So what is forward modeling? So what is forward modeling? Now I have already made the model. Now suppose this is my model. I know this subsurface looks like this. So I know the subsurface looks like this. I know the depth value and I know the velocity. So I can compute the data or other informations like what kind of rocks and everything is present there. So that is called forward modeling. That means from model we are trying to generate the data. So data is given by a parameter operator to give a model M. F is the operator. Okay, so this is called forward modeling. Now, so here, what is forward modeling in this case? So see, I pick the phase first from the first let me explain the inversion or inverse modeling. So what happens? I have the data, and but I do not know how the subsurface looks like, and how many layers are there, or what is the velocity of the subsurface each layer, what is the thickness of each layer. So I have no idea. I only have the data. So from data, if I am trying to prepare a model with velocity information and thickness information and the orientation of the bed, that is inversion. So what I'll do is I'll start with the phase picking, and then I'll try to make a model and try to generate the rays through that, and I'll see if my generated rays are matching with my picked phases or not. And if not, then I'll change the model, try to fit the response, synthetic response with the data. So what is happening? First I did inversion. Now I'm trying to change the model to match my data. So this is forward modeling. So I'm doing simultaneously inverse modeling and forward modeling. So I hope you understand what is forward modeling and inverse modeling. If you have any questions, please ask, or I'll move to next slide. You have to understand this very clearly, because if you will not, then you'll not be able to follow what I'm going to share in the next slides. And also see these black dots are depth nodes. Okay, so the main concept of modeling here is we use the modeling algorithm given by Jelt and Smith 1992. If you can just Google that name, Jelt and Smith 1992, so you'll get a paper. He has explained how to do ray trace inversion. So basically what he states that we take one layer. Now suppose forget about full layer. Now we take one layer. This is the top surface. We assume one layer. Now I pick the phases. I give a horizontal layer for that particular phase. Now suppose I only pick direct phases, direct arrival, and I generated the ray by giving the keeping the first layer horizontal. Okay, if the rays are not generating, so what I'll do is I'll perturb that thickness. I'll change the thickness. Okay, and I'll try to generate the rays again. And if the rays are generated, that means that particular velocity, I'll give the velocity information, the velocity gradient, and the depth. Okay, so there are 3 parameters. So these black dots are depth parameters, and the square is the velocity parameter. Okay, so I'll have to change velocity gradient, and depth also. What is velocity gradient? Yesterday I talked different types of velocity while seismic data velocity analysis. So what happens now? Each layer will have certain velocity on the top and certain velocity at the bottom. So the variation of the velocity from top to bottom is called velocity gradient. Okay. So I have 3 unknown parameters: depth, velocity gradient, and the velocity. So I have to change all these, this, and we'll try to generate rays. And if it is generated, that means this particular thing is correct. And how we do that? So I made one flat layer, and to generate rays, what I did, I divided those layers in many multiple trapezoids. Okay, I'll show how. So this is, sorry. See, I divided this as one trapezoid, then this is another trapezoid, then another trapezoid. It could be of any shape. Okay, depending on how your rays are generating for which kind of shape. So what we did, we divided this particular layer in different trapezoids. So you can see here also, there is one trapezoid. Sorry, this is one trapezoid. So we try to find the velocity and depth of this, then velocity and depth of this, and the velocity and depth of this, and velocity and depth of this, and then we try to compute the velocity for middle point also. So this will give me velocity gradient. So that means, and if this velocity and the depth for each node is correct, and the velocity gradient which I calculated is also correct, then the rays will be generated through this particular layer. And if it is incorrect, then it will not be generated and will not be able to image. Once the rays are generated, that means I have the information, because rays are passing through this. So I have the information of this particular layer, and I'll be able to image that. So hope this is clear. Then I'll move on to the next slide. If you have any questions here, please ask. Or next is only the what do you call, case study, which I'll be talking about. So if you have any question up to here, please ask, because it's going to be very difficult after this. If you don't have any questions, just say no, then I'll move into the next slide. And mind you, this all thing can be done on a free software by and the software name is Rainbow. No questions. Okay. So the wait 1 second. The software name is Rainbow, and it is freely available on internet, and it's prepared by Gelt. Okay, it's prepared by Gelt, and the software name is Rainbow. You can download that. You can install it in your Linux or even yeah, it will work only in Linux. So you can download that, and you can install that, and you can do all this stuff. And the data is also available on the website, or you can download the data from OGL Mars or Seismic Unix website, and you can do this stuff. Okay, so note that. And for phase picking, you need a free software. It's called SES White or Size Earth. So these softwares are very SES White and SES Earth are free softwares, and they are used for seismic data picking, phase picking. And after this phase picking, you can what do you call, do this ray generation in Rainbow, which is also free. Great. Moving on to the next slide. So I have already showed you seismic data, 3-component seismic data for P and S wave combined. So here, this is the P wave. For P wave, P wave also has S wave, but my main focus here to pick the phases for P wave. So I'm showing for only short point 2, and this is S wave. See, I removed the effect of S wave, so my P wave phases are prominent, but you can see here how noisy the S wave data is. So for picking the phases for S wave, we have to be extra careful. So you can see here, you can see here direct arrivals, then refraction, then again one more refraction, and then there is some kind of skip is happening. Then there is reflections are here, and same goes for this. direct arrivals, then refraction, and then what do you call? There is a gap or skip here, which we'll see in the next coming slides with zoom, and then multiple reflections you can see. So data is very clear for R, and that is why our strategy was to pick the data for R first, and then we can go for other other components. Okay, so this is the example for P wave. Okay, and this is the example for S wave. Hope the talk is interesting. Okay, so what we did was we first modeled the data for shallow. Okay, and then we move for deeper portion. So you can see here, this is for short point 1. That was the example I showed for short point 2, but this is for short point 1. And you can see here, it's 200 kilometer long profile. Okay, and travel time is here, and TD by 7 is reduced travel time. Reduced travel time means the assumed travel time. That means the maximum velocity in the upper crust way is up to 7 kilometers. So that is used. So this is called reduced travel time. Okay, and you can see here the data was modeled for up to 15 kilometers of depth. Okay, and as I said, see, this is the first arrival. Okay, so there is no direct arrivals for this, or because the first layer is the first layer is exposed. See, the layer here is exposed, and then there is one second. Yeah, you see here the layer is exposed here, and then there is some kind of basinal structure is happening. Then again it's exposed, and then again some kind of basinal structure is formed. And so that is why there are no direct arrivals. There are the second. It has only second layers. Phases related corresponding to the second layer. So we see here. This is the first arrival, and then there is a skip here in the data. Skip means that there are no data generated through that layer or in that layer. See, if you check, so the green line is generated in this particular layer, but there are no rays generating in this particular, layer. Okay, but the rays are passing through this layer. Okay, but no refracted ray is generating in this particular layer. That means it is hidden, and the velocity of this layer is lower than the velocity of the above lying layer. That is why rays are not generating in this particular, the refracted rays are not generating in this particular layer, and that is why there is a skip in the data. So so skip are always associated with LVL, that is low velocity layer. And after that, again, we see rays are generating in the lower layer. So corresponding to this refraction, and see, and this blue phase is the reflected phases, which we have seen the reflections. So this is the reflection from the top of the LVL. Okay, and this is the reflection from bottom of the LVL. So reflected phases will be generated, but there will be no refracted phases in LVL, and that will be shown in the data as skip. This is an example for short point 7. We see direct arrivals because there is first layer is present here, so we see direct arrivals, and then there is a refractions associated with the second layer, and then the reflection associated with the top of the LVL, and reflection associated with the bottom of the LVL, and then there is a skip here, which you can see very clearly, and then there is a refraction. So that means another refracted ray associated with the fourth layer. Okay, so this is how this is what ray trace inversion does. Means, see, first how I did this. So I picked the phase, okay, from my judgment. Okay, so now I assume this phases are looking perfect, means its phases are present. So I picked those phases, and then I took a straight line like this. Okay, I assumed a straight line, and then I tried to generate rays using the algorithm of Jelton Smith, but rays were not generating. So what I did, I had an understanding of what kind of rocks are present in that particular layer from the geology of that particular area, and I assumed how the velocity will be varying. So I kept a minimal velocity for the top layer, and the velocity gradient I gave of 0.5. Like suppose if I chose 5 kilometer as a velocity for top layer, so I'll keep the velocity gradient as 5.05. Okay, just for my assumption. Okay, and then I kept a horizontal straight line and tried to generate rays, but it's not generating. So what I did, I tried to I divided this into many trapezoids, and I tried to change the depth and the velocity gradient simultaneously, and so as to see. This is my picked phases. So the data I picked this, and the model I made this, and then again I superimposed the synthetic response, which you can see here as a magenta color or black color here. So you see, first I picked the phases, and then I made the model. So it's an inversion, and then I generated the rays in the model, and then I tried to see if my synthetic rays generated for the model I made is matching with the data or not. So it's a forward modeling. So it's a kind of what simultaneous work, forward modeling and inverse modeling. Okay, so meaning to say is we have to change the depth, velocity and velocity gradient for each layer so as to get to generate the rays, and the rays generated rays, synthetic response of the generated rays should match our picked phases. And if it is not matching, that means I have picked the phases wrongly, or my model is incorrect. Then again I have to change my picking and model as well. So it's a kind of iterative process. It means we have to do it multiple times. Okay, I hope this is understood. You guys have understand this. Okay, so now moving on. So you see direct arrivals, then refractions, then reflection, how the reflections is happening. See, in the previous session we saw seismic data processing, and we saw the layers. We got the layers in a stacked form, but it was very it was not that clear. We had an idea, okay, how the orientation of the bed is happening, but here we are able to delineate the orientation of the bed and the thickness of the bed of the layers, and velocity as well. We'll see in the coming slides. Okay, that was for shallow. And then again I did for the deeper portion. See, deeper portion we take only the reflections, because or wide angle, we call it as wide angle refraction or reflection. So for deeper layer I picked the reflections, which are very clearly you can see here for for short point 7 and short point 1. Okay, you can see clearly here. So this PM, so the nomenclature is PM, is the layer reflected reflections from MOHO. And one more thing I forgot to say. See, the refractions and direct arrivals have subscript, are denoted by subscript for P wave, and for reflections are always denoted with superscript. So P2 means reflection from second layer, and P3 means reflection from the third layer. Okay, interface of the third layer. And same as this, so we are only talking of the reflections or a wide angle refraction. So I have taken the superscript because I'm dealing with this reflections only here. So this is the ray generated for this particular model which I prepared, and this is the synthetic response, and it's matching with the picked phases. That means my model is correct, and it's not matching fully, means like my chi-square is not 0. If it is 0, that means if I'll zoom this, you can see here some discrepancy. Okay, it's not zooming further. So you'll see that the synthetic response has some up and down from the picked phases. If you zoom this, you can see here. And if my data picking and synthetic response matches 1 to 1, that means my chi-square becomes 0. That means I have manipulated the model and the data. Okay, so that should be avoided. And now suppose if my picking and synthetic response doesn't match, and my chi-square value is more than 1.5, that means my model is incorrect. Then again I'll have to make the changes. And the thing which you see here is called synthetic seismogram. Okay, so synthetic seismogram is generated to check if my model is correct or not. See what I did here. This was the data. Okay, this was the actual seismic data, and this is the synthetic seismogram I generated using some algorithm. Okay, so you see amplitudes here. You see amplitudes here You can see amplitudes here corresponding to the first layer or second layer or third layer. So you can see the amplitude here. You can see the amplitude here. So it's a synthetic. And for wherever there is a interface is not there, it becomes zero. The amplitude becomes zero. So at each interface there is a presence of amplitude. And you can, the kind of things which you can see here is called triplication, which is generally common for a wide angle seismic thing. Okay, and this is for P wave. Okay, so what we see that Moho is up to the depth of Moho varies from 38 to 48 kilometer of depth. So you can see here how big the explosive size would be to image crustal layers up to Moho. So, and with a great resolution. See, the phases are so clear phases. That means I have used a huge amount of explosive so as to get perfect or very crisp amplitude for even for the deeper reflectors. Okay, this is for S wave. Similar thing for S wave. We see here I reduced same data. I took the same data, but I suppressed the effect of P wave, and we are left only with the S wave. So I picked the phases for S wave, and for the, since I have already made the model for P wave, same model will be used for S wave. And one more thing, picking up the data for S wave is very difficult because of the noise. Because the data for S wave is very noisy, and the phases are not that clear. So it becomes very tiresome and cumbersome and time taking, and for picking the phases. So we have to be very extra careful while picking the S phase. But our work becomes very easy because I already have a model from P wave. Okay, and one more thing. See, the relation between VP and VS is like VP is equal to √3 by S wave velocity is equals to P wave divided by √3. Okay, so the P wave velocity information from the P wave modeling, I divided those with √3, and I used for each node. Nodes are like this. These are the nodes. Okay, so for each node I have P wave velocity. So I converted that for in S wave velocity. So I got the S wave velocity as √3 after dividing by √3. Okay, so I use this velocity, but it will not work because S wave √3 is an ideal case. Okay, S wave velocity divided is P wave velocity divided by √3 is ideal case. Okay, so but our subsurface or Earth is not ideal. So, but what happens? I took the P wave velocity information, I divided by √3, and I got the S wave velocity. I put that S wave velocity model computed in these all the nodes, and then my only work was to change the velocity and the velocity gradient so to a very minimal extent. Okay, so that even by a small change, I was able to get good rays coverage, and which matches my synthetic pig phases. The synthetic response, this black color or the magenta color here, matches my pig phases. So S wave modeling becomes very clear, very easy. So now I have P wave velocity model, I have S wave velocity model for upper crust, and now same procedure was applied for deeper portion as well for S wave. Okay, same thing after dividing by √3, and then perturbing the value of velocity and the velocity gradient, I got this. Okay, and this is a synthetic seismogram for S wave. So now I have a model for P wave and S wave, P wave velocity model and S wave velocity model, and I have the crustal model. Crustal model means the variation of the and the thickness of the each layer. Okay, and this is see, in this reflection and refraction both were there for short point 7 and 1, and in this only the reflections are there. But to be very sure, what I did was I combined refractions and reflection for a deeper portion as well, and we can see here for P and S wave, we can see here for all the short point 1, short point 2, 3, 4, 5, 6, 7 for all the short points, all the 7 short points, and we see a good amount of ray coverage. Means the ray density is very good. That means my model is somewhat okay. But after making the model, I have to do multiple model assessments to be sure that my model is correct or not. See, the 1D velocity model I was talking about, this is the 1D velocity model for each short point I made. This is the initial model which I take, and then I combine the velocity break for each, wherever there is a change in the velocity. Okay. See, you can see here the top layer has a velocity of 5.4, then 6.3, then 5.8. So see 6.3 and then 5.8. That means this is the LVL. Okay. So, and this is how the velocity is varying for P and S wave. So these are the 1D velocity model. It's easy to generate, and then I combined or joined all the velocity breaks to make a pseudo velocity model, which you can see it's somewhat similar to this. And this acts as my initial velocity model, and then I generated the actual crustal velocity model. So you can see here how the velocity is varying laterally and as well as horizontally. And we see here the velocity is higher in this particular area, and some kind of structure is showing with the help of P wave and S wave as well. So this marks the presence of my Chitradurga shear zone. Here also you see some kind of velocity variation is happening with a very crisp demarcation. Here also we see, so this marks my Babudan shear zone. And also here to see anything here, but in S wave we see something is present here. So that is cross-cut granite, and you see how the velocity is varying laterally and horizontally. And this is the underplating mafic layer. Okay, so you see the velocity variation in this effect of underplating in this particular area. Yeah, any questions? No questions, then I'll move to the next slide. Okay, so up to here, any questions? No questions? You understood how I come to this slide? Like, see, I generated the rays by using 1D velocity model. Okay, and 1D velocity model has the velocity information. Then I only have to change part of the velocity a little bit to get the actual velocity model. So which is this. So we see here how the velocity is varying laterally and horizontally. Now you guys will ask why this portion is white and only this portion is varying. That is because only this area has been illuminated with the seismic waves, and this area has not been touched by the seismic wave. That is why it has not been sampled by the seismic wave. That is why we don't have any information of the velocity variation for this. Actually, we do have, but since the ray coverage is only for this, so we are only concerned for up to this area. Okay, so as you see here, see the ray coverage, see the ray coverage, see the ray coverage. So only the area which has been illuminated with the help of seismic wave has been modeled. The velocity model has been prepared for that, for P wave and for S wave. Now I did this. Now how will I know whether my model is correct or not? So for that, I did a ray density count or hit count or model assessment. In model assessment, we have to do what do you call it? Resolution test as well. So we will see. See, you can see here, this is the ray density count or hit count. So we see a very good amount of rays are generated through each layer. So that means most of the layer or the area has been sampled with the seismic data, has been illuminated with the help of seismic data. That means almost 100% of the area has been sampled with the seismic data. That means my model is correct. See, I have not kept the resolution test here in this. I forgot. Okay, but that is not an issue. In resolution test, what we do is we take the value of depth and we try to perturb it to a maximum limit. So, and we try to generate the rays, and the point where it stops generating, so that becomes my limit for the depth. And same goes with the velocity. We take one velocity point and then we note, and then we try to perturb the velocity value to its maximum limit and try to generate the rays. And if and we'll pick a point where the rays stop generating, and then we'll keep our model in that particular layer from where the what you call rays are for which limit the rays are generating in that particular limit. Okay, so that helps in resolution. That is also that is the thing which is called resolution test. Okay, now I have discussed seismic modeling, and now I'll discuss gravity modeling. How gravity modeling is helpful for seismic. So seismic modeling seismic surveys are very costly, very costly. Like for our kind of work, it starts with like 5 crores or like 50, if you don't understand 5 crores, so let me tell you, 50 million Indian rupees or 100 million Indian rupees. So it's very costly. So before going with the seismic survey, we do gravity modeling. We do seismic people also do gravity modeling. So we collect Booker gravity anomaly, Booker gravity data, and then we for the whole area. Okay, so this is for Dharwad, this is the Booker gravity anomaly map for the whole area. Okay, and we see there are like the maximum and minimum value is around almost minus 70 pracoules to 100 milligauss, and we see some kind of sharp variation here. In this particular area, there is sharp variation in the Booker gravity map. Okay, so this is because of the presence of what? Chitradurga shear zone. Okay, and we see the highest gravity anomaly at this particular zone. See, granites have low gravity, but in this close-pit, see, when I model the data, this is close-pit granite. Okay, so here for this we see this is close-pit granite is showing high gravity. So why is that? We'll understand in the next slide. And we see Western Dharwad has low gravity anomaly, and Eastern Dharwad has higher gravity anomaly. Okay, though we see that the seismic velocities are lower in this, that means density should be lesser in this particular area in Eastern Dharwad, and higher densities are present in Western Dharwad. That means the densities gravity anomaly should be higher in this and lower in this, but this is just the opposite. So how should we explain that? And one more thing, while computing this VP, that I'll come later. So now you understand how the Booker gravity anomaly map looks like, and this is our profile, and it has 7 short points, as I showed in the first graph or geological map. Now, how we do the gravity anomaly, crustal density modeling or gravity modeling. See, this is called Nafe-Dirac curve. Okay, this is called Nafe-Dirac curve. So Nafe and Dirac were the first scientists or geoscientists who gave a relationship between P wave velocity and the density. Okay, so I have P wave velocity information from velocity modeling. So for each node, I computed using P wave seismic velocity for each node. I computed the density values. Okay, now I have the density values for each model. Okay. Okay. For each model. So what I did was, see, this is the gravity map was there, and as you can see, this map this is along our profile from Chikmagalur to Perur. See, this is our profile from Chikmagalur to Perur. Okay. And this is the sharp variation at Chitradurga shear zone and higher at the close-pit granite. But what we see here, the thickness is less here. Sorry, I have put the wrong figure of the model here, but it doesn't matter. Just assume that the velocity or crustal model from the P-wave model or SM velocity model I took. By mistake, I put this. So what is happening? See, these star marks are the observed from this Booker gravity map. Okay, and from P-wave seismic velocity model, I computed. I have the information P velocity information for all the nodes. So I computed density for all the nodes, and then I put the density here, and then I try to compute the density. This is calculated graph for this particular density, which I computed from P wave velocity model, but it doesn't match. Okay, initially it will not match. So what I have to do is I have to change these densities in such a way so that these observed and calculated response matches. Okay, and this is done in the graph mode software. It is also freely available, and it can be done on the Linux software. Okay, so gravity modeling can be done with the help, and once we get a good response, so that means my crustal velocity model is completed. And as I said that there's a sharp change in the Bouguer gravity anomaly, demarcating the presence of Chitradurga shear zone, which is present here. Okay, and also there is a sharp change in the Bouguer gravity anomaly for this. So that means another shear zone is present here. What is happening? Sorry. And see, granites generally have lower density, but we see a high here. So why is that? So we see higher Bouguer gravity anomaly at this particular area. That is because of the thickness of the crust is less, and this high is due to the what do you call submoho structure. Okay, submoho structure. Because of submoho structures, we see a high here. And we see the thickness and the density is higher in WDC, but still we see a lower gravity anomaly values. That is because of the submoho material are the thickness of submoho material are less in this area. That is why we see this low. So now what I understand from this, see, if the crust is thin, that means Bouguer gravity anomaly gravity value will be higher. And if the crust is thicker, then it will be lower. I have already discussed this, so not important. This is not important. I'm not going to discuss. Now, lithological analysis. See, I have lithological analysis is done by computing what? VP by VS and Poisson ratio. So now I have P wave velocity information, S wave velocity information, so I can compute VP by VS and also Poisson ratio. And we all know that Poisson ratio and VP by VS are lithological indicator for any area. So I have P wave information, S wave information, so I can compute this Poisson ratio and VP by VS, and we'll see how the VP, this is the map for VP by VS, and this is for Poisson ratio. And we see here how the images are, means there are many structures we can see here which was not present here in this also. Like, see, this is the lithological map for the same profile. This is VP by VS and this is the Poisson ratio. So we see there are lots of structures present in this particular area, and also here also this is close-pit granite. We can see the close-pit granite, presence of close-pit granite here. Chitradurga shear zone, some kind of structure here, and here we see some kind of structure here. Here also we see some kind of structure here also. But these structures were not present in my what? This. See, this looks so simple, so simple. But when I did VPI-VS analysis and Poisson ratio analysis, we see that numerous structures are popping out, and we see how the lithological values are varying laterally and horizontally. So we see higher values in this area when compared to this for somewhat. So, and see, VPI-VS, if VPI-VS and Poisson ratio are low, that means that particular area is full of is felsic in nature. And if I have higher values of VPI-VS and Poisson ratio, that means it's a mafic area, mafic dominated area. It has mafic. See, you see higher values for, except for this place or on the upper crust, we see higher values for this, and as compared to this. So that this is mafic and this is felsic in nature, and we see some kind of anomaly, means highest values are present here. So that means accent. or cementation or metamorphism of the mafic or felsic rocks. So here also we see higher values in this particular region, marking the boundary of Chitradurga shear zone and indicating that it has Chitradurga shear zone has been highly myelinotized and metamorphized foliated zone. Okay, this is this we have plotted. This is our we have plotted VP or VS for P wave velocity and S wave velocity for upper, middle, and the lower crust. So this is for the upper crust, and this red dots are our data points, and this black circles which you see here with the data points, it's a laboratory work. So we see how our data points are falling on this laboratory work. So we see the presence of sedimentary assemblage or volcano-sedimentary assemblage on the top layer, then the presence of quartzite, which means that we have then presence of then felsic rocks, then mafic rocks. Also here first wave also we see felsic and mafic and quartzite, and for this is for mid layer we see felsic. The mid rocks are felsic in nature, which is clear from the this one. See, we in the middle we see the rocks are mainly felsic in nature, which is for mid crust. So which we see here, and for the lower crust we see the rocks are felsic and mafic both. For EDC it's felsic, and for WDC it's Western Thalacaton, it's mafic in nature. So this was lithological analysis. Now I'll talk on about the seismic anastropy. See, I have three components, data from three components. Okay, so I have maximum velocity, minimum velocity. What happens? What is seismic anastropy? Anastropy means like variation of physical property with direction, not with the location, but with direction. Now suppose this is one crystal. So this crystal, if it is anastopic in nature, so if a wave passes through this, and so what will happen? So the rays will be bifurcated, and it will move, it will split, and it will have a certain velocity for one wave and certain velocity for other. So S wave generally splits in an anastopic media. And now suppose if you use P wave and the rays are passing through this like this and coming out this, so the velocity will be something. Now if I put the rays through this P wave and it comes out through this, so the velocity will be different. So that is why the anastropy is the change in the physical property with direction, not with the location. So if I have three component seismic data, that means I have the velocity information for Z, and the two vertical component, and the velocity difference will be obviously there, which you will see. So by using that, we'll have maximum velocity, minimum velocity, and the mean of that can be used to compute the seismic anastropy for any particular reason. See, why seismic anastropy is necessary? It is because every seismic whenever we do seismic modeling, we assume that Earth is isotropic just to avoid the complication of mathematics and algorithm. But that is not the case. Even if there is slight hint of anastropy will be there, our imaging and modeling will be drastically affected. So we have to consider the effect of anastropy in that. And the best way to understand if anastropy is present there or not is by studying the S wave, because S wave splits into two waves polarized in two different planes with two different velocities in an anisotropic media. So that is why S wave is very important. So this is an example for short point 1 and short point 7 for P wave. This is for Z component, R component, and T component. So if we see that there is the phases, the travel times or the phases have different, because since the velocity will be different, then the arrival of the phases, travel time arrival or travel time of the phases will be different. Means arrival, picking arrival, what do you call? First arrivals of the picking of the each phases corresponding to each component like Z, R, and T will be different because they have different velocities. So my motto for P and S was to pick the phases for all the components, which I did already for a modeling of my seismic data. Okay. seismic data. So after the analysis of modeling of for P wave for Z and RT and component and T component, I found that there is a variation in the velocity for Z, R, and T, and we found that a radial component has maximum velocity compared to Z and T. So I used that and I took the minimum velocity, which is the vertical one, because I have to map the anisotropy for vertical slice. So I took the radial and the vertical, and then I computed the anisotropy for P wave and for S wave. Same method goes for the S wave. Okay, I picked the phases for all the components for S wave, and then I modeled the data, and I saw that there is a variation in the velocity. And with the help of that, I computed the anisotropy for P wave, anisotropic model for P wave and S wave, and also see hexagonal anisotropy, or like there are different types of anisotropy. So vertical, transverse anisotropy with vertical axis. Now see what happens. There are many layers on top of that. There are many. Now suppose there are 3-4 layers like this. So if a ray is passed through this, so obviously this whole layer, this whole structure will act as anisotropy. Anisotropic in nature, will be anisotropic in nature. Okay, so then transverse isotropy with vertical symmetry is the most common type of anisotropy present in the subsurface, or we call it hexagonal anisotropy also. And it can be defined by P wave, fast P wave, slow P wave, fast S wave, slow S wave, and VP45. Means now I have only 3 component, like 2 horizontal and 1 vertical. So this, now suppose this is my radial and this is my vertical. So I have the fast and the slow. But to deal with the transverse isotropy with vertical symmetry, I have to compute velocity for 45-degree also. So for that, I need these coefficients. So C1, C33, C44, C55, C66 can be computed from VP fast, VP slow, VS fast, and VS slow. But VP45 cannot be computed. It can only be computed in the lab, because in lab I'll take the rock sample and at 45-degree I'll shoot the seismic wave, and I'll calculate the value, or I'll record the value. But for in situ kind of thing, it is not possible. So for that, I have to compute C13, which is also important, because C13 and C45 are related to one another. So for this, I need this. For this, I need this. But these C13, C3, C44 are called stiffness or elastic coefficient. Okay, and these are required to compute the Thomson anisotropic parameter. See, I computed anisotropy for P wave and S wave, but just to justify that, Leon Thomson gave certain parameters like delta, gamma, and epsilon. Okay, so I have to compute all those things to justify that, okay, there is a presence of anisotropy in that particular area. And for the computation of all these 3, I need this 5 independent elastic coefficient, which can be computed from VP fast, VP slow, VS fast, VS slow, and VP45. Now we'll see how to compute VP45 and VC13. See, from this formula, I used for P and S wave, and I computed this seismic anisotropy for P wave and S wave. We see how seismic anisotropy is for S wave, it's very high compared to P wave, and we see that S wave is giving much more structure than P wave, and that is because S wave is very sensitive to the fractures and any kind of variation in the lithology and presence of fluid. So and anisotropy, because S wave splits into 2 wave polarized in 2 different planes. So S wave is much more sensitive towards anisotropy, and here we see that is why here we see different types of structures for S wave anisotropical model, but which is not present in the P wave model. Okay, and see, this is how C13, C11 or elastic coefficients are computed. Okay, and this is C13, and you see that C13 is dependent on VP45, and VP45 is dependent on C13, and we'll see how it is computed, and it will be very helpful for you in the future. And see, this is the Thomson's anisotropic parameter. This is epsilon. This is associated with P wave anisotropy, and this is gamma. This is associated with S wave velocity, and this is delta. Delta is like is dependent on the VP45. Okay, so computation of delta becomes very much important, and it requires C13. Okay, and C13 can only be computed using VP45, but we don't have that information. But we can compute that. See, for the computation of C13, we take the upper and lower bound of C13, which can be easily computed without considering VP45. And after computing the lower and upper bound of the C13, then taking the average of that will give you actual C13, and then from that we can compute delta. So which is shown here. So this is the lower bound and this is the upper bound of the C13. And see, this can these values C11, C33, C55, and this C12 can easily be computed. Okay, so I can compute upper bound and lower bound, and the average of these upper and lower bound will give me C13. From C13, I can easily compute delta. Now this is an model for epsilon delta and epsilon delta and gamma, and we see the variation of this is up to 100 kilometer I have kept, and anisotropic model which I saw, that was only done for that is also done for 100 kilometer, but because I had only one day, so by mistake I put this instead of 100 kilometer I put this one. So I can send you the image separately after the talk. So, but you see here for epsilon, how the epsilon parameter is varying, and this is corresponding to the P wave, and this is for S wave, how it is varying. But delta has a totally different scenario. You can see here the high values of delta up to this, but here you don't see the continuation of the higher values of gamma. And higher values of epsilon in this, but here you see there is a continuation of this. So this all can be taken and in consideration when dealing with the or making a geological model of the subsurface, which looks like this. Okay, so combining all like P wave, P and S wave information, VPR, VS, and anisotropy, we came to this tectonic model that because of the plume activities which is happening and the plating is created, and LVL is created, and we see how the variation is happening in the ground. This is I'm not going to talk because this is not that much important. This is the evolution of from all these studies, how I postulated or I put forward a hypothesis about the evolution of Eastern Dharwad Craton and Western Dharwad Craton, or all in all Dharwad Craton. So this is all geology. I'm not going to discuss this. So with this, I'll end this talk. Okay, and I'll send all the material to the moderators, and they will send it share with you guys. So I'll send all these things. So if you have any questions, please shoot, and we'll end the session now. Do I need to talk about seismic anisotropy more? Good. I'll show you the actual. One second. Wait, I'll show you the actual image. This. One second. Show you the actual images of the anisotropic 200 kilometers, which I forgot to put here. Yeah, you're welcome. Uh, one second, one second. I'll start with the sharing again. I'll start. How to screen sharing is paused. How to start sharing screen again? Share screen. Which one? Which one? Which one? Wait. I just want to show you one image. Just for that, that is why I'm. Yeah, this was the image that the image which I showed was incorrect there. Sorry for that. So this was the P wave anisotropy, and we see what is how similar the P wave and the epsilon images were, because I already said that epsilon depends on the P wave, and this is for the S wave, and we see what you call presence of LVL in the below Moho also. Okay, and we see this is this S wave anisotropy is similar to what gamma or yeah, gamma. Okay, and we see a totally different structure for epsilon. For these are sorry, Thomson anisotropic parameters. Also, you're welcome. I hope you guys learned something. So sorry, I was looking.
Yeah, thank you very much, Dr. Deepak. It was it was awesome listening to you. I think for now there are no questions.
You
We
can
will have
ask
to go
questions
over
through
the
mail.
recordings and
Yeah, you can share with
we'll have
students.
to go over.
Yeah, you can share with
Yeah,
all the
we'll go
students. And if they ask any questions, they can write to me on
chat
my.
to you.
And yeah. So I hope
Okay,
you
sir.
understood, even if you understood 30-40% of what I delivered, I'll be the happiest person in, I'll be very happy, because, when I was in masters, and any scientist or any person to come and give, you come for any kind of lecture, I'll be like scratching my head what he's talking about. Oh my God, I don't understand what he's talking about. And what kind of questions should I ask? I have no idea. So even if I try to keep it simple, and if you even if you retain 30% of 30%, I'll be the happiest teacher in the world. I'll be very happy. So I hope you understood something. See, I gave you the very basic and fundamentals of seismic, and now you can utilize these concepts. And when you go to your books and read, you'll be familiar with all the terms, and you'll understand everything. And one more thing I'll tell you now. Suppose if you are reading a book, or your book, or seismic method from your book, and if you don't understand any concept of the book, you can always reach out to me. Okay.
Okay, sir. Thank you very much.
Yeah. And I have already shared the signature and everything for the certificate. Please use them to provide the certificate to the students. And one more thing, I'm going to post about this workshop on LinkedIn. So feel free to comment on it. So by night, I'll be able to complete that on the LinkedIn, so that now I'm trying for postdoc, so it will help me in my postdoc application. So I'll write a LinkedIn post. Please try to comment if you learned anything. So,
okay, sir. All right, I will definitely do that. We're so happy for it's been roughly 1 month now, and it's really a nice ride. I love the way you were breaking down every step to the basics. You were really giving out the principles. So we just need to go over them, assimilate them. We can come with our questions, and we'll surely get back to you, sir.
Yeah,
I don't know if there are quizzes attached
yeah, yeah,
to
yeah,
each of
yeah,
the
yeah, yeah.
sections.
Okay.
Okay, so
Yeah,
we'll attend to
sure.
them and then reach out to you, sir. So
Uh,
thank you very
Sorry.
much, and then to our
Yeah,
audience,
yeah, yeah,
we
yeah, yeah,
thank
sure,
all
sure.
the students that are joining, and most
I,
of us are there's poor network
I,
in this in this part of the world. Yeah, so many students are not able to join the live section.
no
So
issues,
they
no
will,
issues. You can share the videos with them on Google Class, or they can utilize that. And I'm really happy with the kind of initiative you guys have taken. See, when you don't have the classes going on in your place, so you all the student SCG student chapter came together with this idea to learn while the classes are not going. So it's it, yeah, it is. Actually, I thought yesterday I will not be able to complete the processing part. So, but I did, and today was the modeling part. See, I am not an expert in interpretation. See, I know how it works, but I'm not an expert in seismic interpretation. So that is why I didn't take. But if you guys want uh, to learn about seismic interpretation, you need to have that open text software. And then I will give you a name of a person who is expert in that. He's my senior. I'll give his name, and he will be very happy to teach you guys. Means he's such an awesome person, and he is excellent in seismic interpretation. So download that open text software, get the student license, and then write to me. I'll ask him, and I'll give you his email ID, and I'll refer also, and I'll ask him to give 2 or 3 sessions for the same. Okay, and in meantime, please install that Seismic Unix and work on it. It will increase your CV. It will increase the weightage of your CV. Mind you, when I say no, it doesn't matter how in what commercial software you have worked upon. But if you go for postdoc or any PhD admission for any Ivy League institutes from UK or US, if they see that you have seismic Unix in your CV, that you know the concept of seismic Unix and you know seismic data processing by using seismic Unix, they will take you like this. Means you'll be the first person to take to get the admission in those colleges. Okay, that is why I'm again and again I'm emphasizing on to get that Seismic Unix install. And if you face any kind of installation problem, I can take one session on that, the installation of Seismic Unix, how you can install. Or if you type on YouTube installation of Seismic Unix, you'll get the video. There are lots of videos are there, and even in Google the steps are mentioned. So you just follow that steps, download and install. I'll say that better to download like VirtualBox of Oracle, and then install Ubuntu on that on VirtualBox, which I'll show here. 1 second. Wait, I'll share my screen again. Then what happened? What happened? I'll share my screen and I'll show you how it is done. Okay, so this is VirtualBox. Where is it? Yeah, Oracle VirtualBox, or VMware is also there. So you have to download VirtualBox or VMware. But VMware is costly. VirtualBox is free. So better go for VirtualBox. So VirtualBox looks like this, and just click on new, and then you can install Ubuntu. So I have already installed this, so I'll show you. And I also have so second, what happened? Yeah, so it's starting. Ubuntu is starting, and then on Ubuntu, just go and type Seismic Unix, and it will be downloaded, and then you can install, and you can get the manual from the same page. You can get the data from the same page, and you can start working. And we can, if you, whenever you have doubt regarding the steps of seismic data processing in Unix, I can help. all the commands necessary for seismic data processing using Unix is in the manual provided by the same page. So you'll not face any problem. You'll only face problem with the processing steps, which I have already discussed. And whenever you face any problem with that, I'm here to help you guys out anytime, any day. Just give me a ping or email me. I'll help you with that. Okay.
Okay. Thank you so much, sir. Thank
So
you
now
so
you
much.
understand how the virtual box works. So do that. You can use Seismic Unix. Okay. So if nothing is
Okay.
part ways, and hope to meet you again and do well in your academics. I'm getting old, so but it was nice, really nice talking to you guys.
Thank you so much, sir. So I don't know if our audience they can on their videos. We could take a snapshot.
Snapshot of.
Like the audience, everyone.
Okay. Okay.
Okay. All right.
Okay. So shall we leave?
Yes, sir. Thank you so much.
Thanks a lot.
So bye everyone.